of the Royal Institution of Naval Architects, the Institute of Marine Engineering, Science and Technology, and Engineers Australia. Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures and to elders both past and present and emerging. Our presenter this evening is Clive Evans. Clive is a naval architect originally from the UK, but now living in Hobart. He has a background in the design and construction of roll-on passenger vessels with periods of employment at Holder Limited, Lightning Naval Architecture and BMT Nigel G. In 2017, he joined the Australian Antarctic Division's Nuyina project team, where he provides technical support to the design, build and commissioning process. Ladies and gentlemen, I'll pass you over to Clive Evans.
Thank you, Phil, for the introduction, and welcome to everyone who's watching tonight. So first of all, I'd like to start with an introductory video to the Australian Antarctic programme. Okay, so start with an overview of my presentation this evening. The first thing I'll be looking at is the Antarctic programme shipping requirements, and then the drivers for our new shipping capability. Following that will be an overview of the RSV Nuyina and the construction update of where we're at today. The final part of the presentation, I'll look at some technical case studies, the contract format, propulsion system design, wet well sampling space, the scientific space we have on board, and finally we'll look at the DP and cargo resupply process. So starting with just a bit of background on our shipping requirements. One of the fundamental things that we do is resupply our research stations with fuel and solid cargo. This map is a little bit difficult to see, but it shows the three main stations we have on the Antarctic continent, as well as our station on Macquarie Island, and also our territorial area of Heard and McDonald Island. So if I start, first of all, this is a visual shot. We'll quickly go through some of these photos just to give you an idea of what we do. This is our Casey station and a resupply activity going on there using landing barges to resupply solid cargo. This is our Davis station, which is often ice locked in the early part of the season when we visit. This is a helicopter resupply activity. And this is an over ice activity, which was actually last season. As you can see, this is an installation of a new crane, mobile crane in Davis, by loading it onto the ice and transporting it over the ice to the shore. And our final station on the continent, Moreton. Here we actually currently anchor in a harbour, but this will change a little bit with Nuyina. But this is a deployment onto a barge where we then take it ashore. And this is a fuel line transfer of fuel ashore at Moreton. Finally, our sub-Antarctic station on Macquarie Island. This is a different process completely because of the lack of over ice or barge resupply possibilities. Because of the lack of a key, we actually use amphibious landing craft just for this station alone. Another fundamental role of our program is to transfer expeditioners. One of the ways we do this is via the A319 to the aerodrome, but we also critically, and most people arrive via ship and an IRB shore transfer. One of the things, because of the isolation we operate and the people that we have, one of the key areas we have is medical, and this is just a quick shot of the medical facility that we have on board the Aurora Australis, the outgoing vessel. We also have an important role in providing a marine science platform. Some of the operations that we do, here's a shot of a stern trawl, a very old shot of a stern trawl on the Aurora Australis. This is the fish sampling and monitoring population numbers, for example. We also deploy CTD units, which measure the conductivity, temperature, and depth of water. This is important for salinity measurements and monitoring populations and what effect salinity may have on them in the future. We also monitor krill, with it being one of the most fundamental parts of the ecosystem in Antarctica, as well as observing whales, seals, and other marine mammals. And another activity that science undertakes is an atmosphere and light monitoring process. So all of this is really to support the marine environment and marine science operations that we do, which leads to information on real important issues, for example, climate change. Lastly, we have a small design driver in that we do have a secondary government support role. That's principally a humanitarian process to potentially help in those sorts of situations. So moving on, the drivers that we have for a new shipping capability. The Aurora Australis has now done 30 seasons in the Southern Ocean. In fact, she's actually finished her service now with the program. We have a 20-year Australian Antarctic strategy, which requires increasing cargo capacity and a lot of asset refurbishment. So because of that, that drives a lot of why Nuyina is the size and capability that she is. Due to the fact that we're increasing our cargo capacity, we will typically expect to see a change in our program, which for those of you who are familiar, is currently a one voyage, one station in principle, but we are now looking potentially in the future of doing more than one station per voyage because of the ability of this new vessel. So because of that, that will free up more operational days during the season and expand the marine science sector, which is currently very limited on the Aurora. So really this process is all looking at ways of freeing up time to provide more time for science. And finally, that's it, and greatly improved science facilities, which I'll go through later. This is just a quick shot of the comparison of size with a real shot of the Aurora Australis in Hobart and a rendering of Nuyina, showing the change in length, but it's actually really the displacement and capability that she has that's the real improvement. And I'll just bring up this graphic here. It's very hard to see over the presentation, I imagine. But this fundamentally is the sort of 3D presentation of Nuyina. I don't think I can point on this screen, so I'll just, at the aft end of the ship, we have a trawl deck for overboard deployments and the heli deck on top of that. Moving forwards, the helicopter hangar is on top, and underneath that is a variety of watercraft for science or personnel deployment. And moving forward from that point is the main accommodation area on the ship and the bridge. And forward of that is our two main cargo holds and our two cranes. Forward of that further is our overboard deployment, which you would have seen on the video. The next slide gives you some more technical overview. She's 160 meters long and 25,000 tons displacement, which is around 3 times the Aurora Australis. 30 megawatts of installed power, of which 26 is dedicated to potentially propulsion power. 12 knots an economical open water performance, but a potential for 16 plus knots. Range of 16,000 nautical miles and 90 days. And a bit more on the sort of standards we use. The DEFOS 5000 standards being used for seakeeping. Icebreaking performance is contracted for 1.65 meters with various snow loadings at 3 knots. She's DP2, silent R notation equivalent because that's the DNB notation and we are LR class. 32 crew and 117 passengers. Those numbers are similar to the Aurora Australis. This is an overview of some of the science systems that we have. Starting at the 12 o'clock position, we're monitoring upper atmosphere and weather. We also have observation points for marine mammal and seabird observation. On the forward mast, we have an aerosol sampling system for atmospheric measurements and water sampling system at the bow for the clean flow of water. We also have subsea acoustic systems for seabed chartering, and we're able to deploy various instruments to measure underwater properties via either the marine pool or the CTD door on the side. And as I've mentioned already, we have a full deck for either doing sampling or deployment of moorings or whale buoys. This is a bit of an update of the construction. If I start at the top left position, this is our keel laying ceremony. We then move forward to a milestone of all below bulkhead deck blocks in the dry dock, the installation of the propeller shaft, the float out, which interestingly you'll see we have some sort of inflatable bags there to reduce the displacement to get it over the dock wall and correct trim. So that was quite an operation to flood the dock. Moving left from that dock position, we have the installation of the bridge module, which then finally led to the completion of all steelwork. Now that's reasonably outdated now. The easiest way to summarize this is to show you a video of the progress which was taken in April 2020. I'm going to share my screen for doing this because so apologies for those if that was a bit jerky. That video size we had problems with earlier. That video was taken in Galat Shipyard, in Darman's Galat Shipyard, which is where the ship is currently being built. And it felt it was important to show the video because it really does give you a feel for where we're at with the project. This is a bit of an overview of the test program, and no presentation at the moment would be complete without a reference to the COVID-19 situation. So some of these dates have changed due to the current restriction on travel, and most of these tests, as you probably appreciate, would require OEM support from various manufacturers in Europe mainly, and travel restrictions do mean that those tests are currently delayed. So we are currently undertaking harbour acceptance trials. The last harbour acceptance trial was conducted on Saturday, which was actually the inclining experiment. So that will give you an idea of how advanced the ship is now in its construction. That was a first for me, attending an incline via webcam, but it was, it's certainly a good indication of where the project's at now. The commencement of sea trials was scheduled for mid-2020 and special sea trials in the Arctic Circle mid to late 2020. Arrival in Hobart follows the completion of the special sea trial program. The reason for the special sea trial program is essentially because of the icebreaking performance and cold weather performance of the ship has to be undertaken in the specific environmental conditions. It makes the sea trial program somewhat more complicated compared to a conventional ship. So I'm now going to move on to some case studies, some technical case studies on some systems on board, which relate to naval architecture and marine engineering. The first one is the contract format. Now, we actually have a DBOM contract, design, build, operate and maintain, with our prime contractor, DMS Maritime, who are now part of Serco Defence. That contract was signed in April 2016. Fundamentally, on the technical side, we have 1,202 requirements, which were included in the contract, but they actually remain in the contract for the duration of that time. Currently, that's a 10-year operate and maintain phase. So a usual process that these DBOM processes follow is that they will actually evolve into a ship technical build specification, but in this case, by including these functional performance requirements throughout the 10 years, we actually ensure that they're maintained throughout that period. Each of those requirements have a technical verification strategy, so that would be a design, a harbour trial, a sea trial, or a special sea trial, depending on the nature of the requirement. And as I've said already, each of them continues to be in operation throughout the operate and maintain phase, where Serco have a contract for 10 years. Now, some of the strengths, I'm just doing a bit of a comparison of strengths and challenges with this form of contract. This is certainly a new type of contract for me in the build process. The strengths of it is the certainty of fixed price and defined performance over the length of the contract, which is important if we remember that it is a government procurement. It is different to a more commercial environment. Also, because we have a prime contractor, it allows our full-time team to be only 6 individuals on the technical side, which we wouldn't be able to deliver without the support of our prime contractor. Nuyina will remain a Commonwealth asset, and the AAD maintains a small team in the O&M phase, which will give us a better connection between ship operations and the owner and the operators. Some of the challenges that we have is that because we're in a tripartite arrangement, we have Damen Scale Shipyard in the Netherlands as the main shipbuilding contractor, Serco, who are our primary contractor, but also Damen in the Netherlands have contracted Damen Galaxy in Romania on the Danube to build the ship. So because of that, we have various layers in the technical discussions which can complicate things. We have also found that there can be a little bit too much emphasis on these 1,202 requirements, and of course other things of importance such as general shipbuilding best practice and quality outside of those requirements. And the other thing we have found is that the size of the team is slightly larger than we expected. I think we have 1 or 2 more technical staff than was originally foreseen, just because of the quantity of information that is transferred between the parties. So that's just a bit of an overview of the type of contract that we have, and shipbuilding contracts are always very different and always can be quite difficult, but it's just an idea of how it works for our project. The second case study that I'd like to look at is the propulsion system design. Now, in terms of design drivers, there are some key differences to what we're looking at compared to what we've had in the past. One is the redundancy aspect, which have a lot of improvement on the Aurora Australis. a heavy ice-breaking performance with ice milling, or the ability to deal with ice that passes through the propeller race at 3 knots. The ability to mill ice astern, which we've looked to improve from the Aurora Australis. Acceptable performance in open water transit, accepting that this is primarily an icebreaker, so there is always a compromise with the open water performance. We're looking as well at a large variation in hotel load, which does have an impact on the propulsion system. Now, typically that would be because of the heating and heat, ventilation, and de-icing aspects that we have on board. They do vary enormously depending on the environmental conditions of the day. LR class notations that drive the propulsion system design. We have a DP2, we have crew comfort, and we have a PSMR redundancy, a propulsion steering machinery redundancy, and an eco NOx and SOx notation. So all of those will drive the design of our system. We also have an IMO Tier 2 compliance and the DMV silent R notation equivalent. So I'm just going to run through some slides of, this is an overview of our propulsion system arrangement. So you'll see we have 2 engine rooms, a forward and aft engine room. The forward engine room has 2 generators and a main engine, and the aft engine room has the same. There is a slight difference in size between the 2 forward ones and the 2 aft ones. But we also then have a complete redundancy in the propulsion train, 1 port, 1 starboard. And where the propulsion shaft on the port side passes through the starboard and the aft engine room, it's completely separated, both fire and flooding sense. So it's completely isolated and completely redundant system. For the heavy ice-breaking mode, we actually have 2 main engines circled in blue there, which are, you see at the bottom. Actually, I can't see that. I've got the size written on the bottom there, but it's cut out on me. And we also have 2 3.7 megawatt PPIs, which we can use to take power from the generator steps to add to the propulsion shaft line. As well as that, due to the ice milling requirement, we have 2 inertia flywheels connected to the gearboxes after the main engine. So they actually increase the inertia of the shaft to allow us to keep milling the ice while it passes through the propeller race. And like all icebreakers, we have a CP propeller. That CP propeller is necessary because of the huge variation in propeller advance speed that we have compared to open water or icebreaking. In light icebreaking conditions, the speed will be much higher, and heavy icebreaking much lower, and open water will be faster still. So the only way to deal with that is a CP propeller system. Of course, the propellers are designed to deal with the ice loading that they see and have the ability to feather out should ice blocks become entrained in the propeller. This is just a bit of a view. That's that shot again of the propellers in the dry dock. We also have a nice knife design on the stern, which allows us to push the ice out the way as we're reversing. Now, reversing is particularly important on an icebreaker because we have to often break out of our own channel should we encounter a ridge or need to adjust course. This is just a shot of the, I think that's actually a cavitation tunnel shot showing the testing that we did. And as I've explained already, the advance speed across the propellers varies enormously between operational modes. So we need to have the ability to adjust the pitches. Now this video is just a shot of the one of the runs of the ice towing tank. A lot of you may not be familiar with an ice towing tank. I'm lucky enough to have spent a bit of time at Hamburg in their facility. So I'll just show this video now. So moving back to the hotel load side. Because of we have a huge variation in winterization, mainly in HVAC, but also in de-icing systems. So, for example, at -30, we have a huge requirement to heat the ship to keep everything from freezing, keep the decks from freezing solid, keep doors from freezing closed, and also heat the space to an acceptable level for it to be habitable for crew and special personnel on board. Converse to that, other days in Antarctica might only be around 0. The hotel load will be vastly different. So what we have is 2 generators, which are both 3 megawatt in the aft engine room, and we have 2 in the forward engine room. Although they appear the same number of cylinders there, they are actually a 3 megawatt and a 2 megawatt, one a 9-cylinder, one a 6-cylinder. We also have the 2 PTOs, which actually also the same as the PTI, because we have what we call an advanced electric drive, which has the ability to take in or put out from the main engine's power. So this gives us more flexibility. We actually can use those as generators on board. And just a bit to say on the notations that we have on there. Some of the unusual consequences of design that we've encountered. Waste heat recovery and economizers are only fitted to the genset. What that means is that practically, because we have a huge use for waste heat, we actually find that the most efficient mode for open water would actually be a diesel-electric situation. So the next line, with main engines, will actually be rarely used. So we actually, although they're called the main engines, they will be used a lot less in terms of running hours than the gensets on board. Will most probably be a diesel-electric ship on most occasions. Now, regulatory-wise, because our main engines are rarely used and the power that they contain is rarely used, our service tanks are considerably smaller than the regulations require, and the capacity to carry oil bills is also reduced. So what that actually means is that we've had to get exemptions from the size of those tanks because they would be unnecessarily big. The other thing about icebreakers, which is an interesting design consequence, is that because we have very high installed power, we do have a very high open water speed, probably around 20 knots, we think. Potential rule difficulties we have with that is that the IMO regulations on manoeuvring tests require that you have a certain high power input, and that means that the speed of entry into our manoeuvres would be unrealistically high. So that's something we've had to deal with during the trial program, and that the scantling requirements are all derived for a speed of around 16 knots. So we are actually limited in our ability to do those speeds because of the notation we have. So that was the propulsion side. If you have any questions on that, please add them to the Q&A section. The next case study I'll be looking at is on the science wet well sampling space. Now, this is an interesting novel concept. This is something developed by the scientists at the Australian Antarctic Division. It's a brand new concept that we would actually take seawater and any fish or sponges or jellyfish that happen to be in that flow and put them into a filter table where scientists would actually observe them and potentially collect specimens. So this is a really exciting concept for our science teams here. We also have an egg sampler, which will actually sample egg numbers in seawater, which will allow us to monitor populations. So the reason we do that is to understand changes in the environment, changes in the ecosystem, and potentially which may or may not be driven by climate change. The reality is, though, we are actually putting 370 tons of water into this space. This space is below the waterline. It's between the 2 engine rooms, and there's people working in there. So this actually creates quite an interesting naval architecture and marine engineering challenge. The water is also at -2 because it's nearly frozen in many cases. So the key thing is, how do we ensure that what goes in goes out under all circumstances and that we don't have a flooding situation? Initially, the concept design proposed using floor plates. So what you see in here, the gap between the top of the floor plate and the floor as a buffer between the inlet and outlet flow. However, we were slightly concerned about this because if the valves didn't shut off in time, there would be a real risk that we would have a flooding situation. So what we now have is a 30-ton capacity drain tank, which is well below this point in the double bottom, and that allows us 5 minutes between the outlet pumps not stopping the work and the water level rising. So it's all automatic, and there's a 3 or 4 redundant systems in there to make sure this happens. But even in the event of that, the scientists or people working in there have 5 more minutes as well to monitor the situation. So multiple levels of safety given the high concept nature of this. The pumps we have are the 2 biggest pumps on board. They're 500 cubes an hour, and they're 500 each. So they're well in excess of the 370 inlet. These pumps, as I said, the biggest on board, and they also double up as the drencher bilge pumps for our firefighting system in our cargo hold. So that's a really new and exciting prospect. Some of the work in the development of that system has also been done at the University of Tasmania. So it's been a real collaborative science effort here in Tassie. The fourth case I'll look at is a resupply case. Now, resupply of our stations is really one of our prime functions that we have. You'll see a shot there of a cargo barge being loaded from our cargo crane. We have an increased capability with Nuyina in that we have DP, which the Aurora Australis didn't. That is going to increase our throughput, we feel. We also have a counterballast system for both of our cranes, which we hope will allow us to keep the ship level at all times. And what that means is not only does it increase the comfort of everyone on board, because we also have the ability to keep the helideck operational throughout that process. So we may be able to resupply via barge and helicopter at the same time. Another interesting challenge is that we're fairly unique in that we open our cargo hatches at sea. None of our stations are considered to be ports, so we actually have to have the ability to open weather-tight hatches at sea, so that has a load line consideration. We also have our landing barges, which have to be able to be lifted on and off the top of the hatch. And you may have seen in the earlier concept rendering, the landing barges are kept on the aft of our 2 cargo hatch lids. So we have to have the ability to crane those on and off. So that's really the limit of our cargo crane lifting ability. So a key thing that we have with our resupply functionality is several design considerations. In the event that one of our stations, which does happen and has happened frequently, is locked in due to ice so our ship can't access it, we have the ability to respond in a couple of different ways, which the Aurora didn't have, the Aurora Australis didn't have. The cargo at the top of the hold is intended, if the cargo on the top of the hold is intended for the locked-in station, it can be moved internally to allow other stations to be resupplied earlier. So, for example, if we plan to visit Casey first and then Davis, if Casey's locked in, its cargo is going to be on the top because that's the easiest way to load it. However, if we need to adjust the plan, we can, because we can move cargo internally via a system of elevators and corridors to actually unpack it and then resupply it. The other thing we can do is break it out into small items, and we can actually then load it up onto the helideck also through internal corridors and elevators, which means we could then deploy helicopter lifts from either the helideck or the forward lift-only point, or both. So it's really an increased flexibility that we have for resupply that we didn't have with the Aurora, and that's all driven by the need to be able to resupply multiple stations at once. And the final area we'll look at is some of the watercraft that we have on board and how they function. Nuyina carries 3 personal transfer tenders. They're primarily, as the name implies, for transferring expeditioners to station ashore. We have a science tender, which is the small vessel on the left. Now that's a mini survey vessel that allows us to do subsea work, but also tow body work. It's essentially a similar system that we have on Nuyina, but it allows us to get much closer to the shore in much shallower water. And the bottom right picture is our 2 landing barges. They were built in Hobart, and they've now been shipped to the Netherlands in preparation for joining the ship later on. Those are primarily load on, roll off, and the idea is that we would crane some of our heavy vehicles and containers onto those barges, and then they would be rolled off at the other end. Again, that will change to what we do at the moment, which is everything has to be loaded onto the barge, and then shore cranes have to lift it off. The key thing is that we're very limited by weight that we can lift off with these containers, but having this RoRo system will allow us to increase the cargo weight, container weight for resupply. So the personal transfer tenders can carry up to 8 passengers at a time, plus the crew, the boat crew that is. The landing barges are designed for a Hydrema 20-foot container handler. Well, I've mentioned about the science tender. It's a 10-metre boat that has the ability to do science operations. So in summary, before we move on to the question area, it's really not just a modern Aurora Australis, it's a real change in approach that we're looking at in the Australian Antarctic programme. Vastly increased capacity in cargo, helicopter operations and science. Very significant investment in our Australian Antarctic programme. This much complexity in a relatively small platform has led to design challenges and will require smart operation in the future. So we're looking at a process where we look at initial operating capacity and then fully developing Nuyina's capacity in the coming years because of the complexity that we have. And all this really makes it one of the most eagerly anticipated ships in recent years. So thank you very much for that, and we'll move on to questions.
The first one is from, I think I lost it. I've got to go back up here. It's from Gary Speechley, who says, what will be the fate of Aurora Australis?
Yes, I thought that might come up. So well, obviously, we're on the Nuyina project. Aurora Australis is owned by P&O Maritime. It's not a government asset. So as I explained previously, Nuyina is a government asset, will be owned by the Commonwealth and operated by Serco Defence. But P&O Maritime own and have operated the Aurora. So really it's up to P&O Maritime what they do with the ship. It's finished with the Australian Antarctic programme. It won't be, well, it shouldn't be it won't be operating with our programme, but what happens to it, I can't say at the moment, I'm afraid.
Okay, Jason Stewart said it's not really correct or appropriate that Silent R is still a claim. That's the intellectual property of DNVGL, who have not been engaged. So that's actually a comment. The next question, the next one is also a comment from Commander Jason Middleton, who says it's interesting to see that DEFOST 5000 is being used for the icebreaker classification. Peter Woodward asks, do you monitor any of the ship's structure or internal systems for fatigue analysis or predictive maintenance?
Yeah, can I approach a couple of those, Phil?
Oh, I should have let you answer those.
That's right. So DEFOST 5000, we've voluntarily entered into that process, and so we followed the standard and we have had it met, but obviously it's not assessed because it's a military standard and we're not a military vessel. So we've used it as a benchmark, which is actually similar to Jason, my former colleague's question on the Silent R. Again, it's followed. DNV, I believe, are going to issue an equivalent certificate, but of course they're not as a consultant. So that's a DMV consultancy, not a DMV class. It isn't DMV class, so it can only have an LR notation. And Phil, I missed the last one that you had.
Peter Woodward asks, do you monitor any of the ship's structure or internal systems for fatigue analysis or predictive maintenance, etc.?
Yes, there are strain gauges in the ship to monitor structural fatigue. So it's monitoring so as well as it just being designed to class rules, it also has strain gauges, and we can actually monitor the loading on the ship. Yes. Right.
Okay. Robert Hayes asks, were propulsion batteries considered as part of the design?
I joined the project in 2017, so I'm not actually entirely sure. The challenge that we've got is the huge quantity of power that we have. 26 megawatts is pretty large. So I don't think it would work for anything that is other than manoeuvring, to be honest. And that's not something I'm aware of it being considered, no.
Right, okay. Joanna Mycroft, hi Joe, asks, for the wet well sampling space, for the water intake and output, are you subject to similar regulations as ballast water? How do you ensure that you are not contaminating water with new species?
Sure, yeah. So the wet well sampling system is water out and in at the same time. So it's an immediate circulation of water. We do also have holding tanks on board for any seawater that we collect that we then don't discharge outside of area. So we do have quarantine, well, they're not called quarantine tanks anymore. They were for a while called quarantine tanks, but we do, you get the idea, it explains the process. We don't discharge seawater or where we've taken it from any location to another location. So that is effectively the ballast water convention, in that we choose to collect and not discharge our seawater rather than treat it. In terms of ballast water, we treat it, but in terms of our science seawater systems, we retain it.
Right. Jason Stewart asks, are any of the watercraft built in Australia?
Yes, the landing barges were built here in Hobart. They're aluminium craft that were built at Taylor Brothers here in Hobart. The other two craft are both aluminium as well. They were built in Norway. Well, actually, the hulls were built in Latvia, the fit out in Norway, because of the expertise in and because it, of course, winterized for operations in ice and cold environments. So they were given to or they were contracted by Garmin to a Norwegian company.
Right, okay. And Mick Dunn, hello, Mick, says, who will be operating the vessel?
The operators, ship managers, are DMS Maritime, Serco Trading and Serco Defence now.
Right. Ashok Parsatam asks, how thick an ice cap can it break or cut?
The answer is I don't know yet. It's designed for 1.65 metres of ice at 700 kilopascals strength and a 0.3 metre snow coating. Snow has quite a large resistance factor on top, but that's at 3 knots. That's a contract condition. However, almost certainly she'll exceed that in terms of her ability to break ice, because ridges may be a few metres thick and she'll need to better break them. So we'll exceed that requirement, but that's our maximum contract requirement.
Okay, Mohammed Kamran Malik asks, what's the load ratio for load versus actual ship? I presume that means dead. What's the dead weight?
Yeah, 16,000 ton light ship, 25,000 ton displacement. So she has 9,000 ton of dead weight. But of course, that will include fuel, ballast water if needed, cargo, fuel, cargo, solid cargo, and anything else we have on board, really.
Okay. Scott Balestra asks, was there any requirement for Australian-built components?
Yeah, that's been a feature, and there has been a feature during the project. The difficulty we've had, of course, is that it's a specialist area doing icebreakers, and it's not something that we've done a lot of. In fact, the Aurora Australis was the last one 30 years ago. I believe it was considered, but I can't really speak entirely of it because I wasn't involved in that stage of the project, I'm afraid.
Okay, thanks. Mike Priestley asks, is the LRAA notation for dynamic positioning similar to the IMO DP3 notation?
No, I think it's DP2. So any one failure can't lead to any loss of a loss of position. So we have the ability to take any one failure, and it has no effect on the DP station. DP3 is more than that. I think it's multiple failures, and it can still hold station. So I think DP3 is normally, unless I've gone the wrong way around, more reserved for dive ships, where someone's light is hanging off the end of the ship, and if the ship loses station, people die. In our particular case, it's more that we have enough redundancy that we can hold on station for resupply.
Right. Anup Rajendran Nair asks, what is the expected design life of Nuyina?
30 years.
Okay, that was a very quick one. Thank you. Mick Dunn asks another one. He says, single crew or multi-crew, i.e. port and starboard?
I'm not sure I understand that quite. I mean, there's 32 crew on board. We have 2 swings of crew to allow us to do the back-to-back resupply operation. The exact number of crew will vary depending on what operations we're doing. 32 is the most, and it's 2 swings, so 2 captains, 2 chiefs, etc., etc.
Right, okay.
And on board at the same time, so it is just 2 completely dedicated swings.
Right. Roshan Manageddon asks, do you have any information regarding Davis Aerodrome project and logistics supply from Nuyina?
Nothing I can share here, I'm afraid, no.
Okay. Subhrajit Sinha asks, what is the estimated cost for the vessel?
So I mean, it's public information. The contract is $2 billion for the 10-year operation. That's build, and that's design, build, operate, and maintain for the first 10 years.
Right. Mahinda Nayar asks, are there any special requirements for the helicopter in the harsh environments?
In terms of the ship, the heli deck is heated, believe it or not, 0.5 megawatt to heat the heli deck to keep it ice-free. And the hangar's heated as well. All of the systems, the navigation systems, light systems are all rated for cold climate. The helicopters themselves, we have a contract with a third party to supply the helicopters. Nothing will change effectively with that because they're used to operating in the same conditions with the Aurora. And that's their level of expertise. I'm not a helicopter guy, so they obviously will have winterization as well.
Right. Rex Burkhardt asks, what helicopter will be embarked?
A Sikorsky S-92, or then there's 2 of them, or 4. I forget the smaller helicopter off the top of my head. There's 4 smaller helicopters or 2 Sikorsky S-92s.
Right. Mike Priestley asks, regarding the open hatches, do you have an operational load line exemption for such occasions, or how do you cope with that?
Yes, it needs to have an exemption. Yeah, it needs to have an exemption because we're not in port. So in order to open, we also have a side door which we can open to deploy scientists onto the ice and to study ice flow. So they're also watertight doors, weather-tight doors, so that we're opening at sea. So yeah, there is an exemption from load line, or will be an exemption from load line, as is usual practice for any supply ship in Antarctica.
Right. Mahinda Nayar asks, what do the helicopters do?
Yeah, okay, apologies if it wasn't clear in there. Occasionally personnel transfer, but the most important role is to carry underslung cargo ashore. So we can break them down into 1 ton pallets that we then crane off, we then lift from the helicopter, either off the heli deck or on the forward hatch covers, we actually have a winch only point, and we can run helicopters simultaneously because of the length of the ship, we have the ability to segregate the helicopters.
Okay. Michael Zagoznik asks, has crew comfort in heavy seas been considered in the design of the vessel?
Yes, so in terms of noise and vibration, we do have a crew comfort notation, but we also have what I would call a flume tank. But it is a flume proprietary system we have, but it's a roll stabilization tank that we have on board as well. We're also, because of the seakeeping test that we're doing, we've also looked at that and what impact that will have. The fact the ship is bigger, the fact it has a flume tank, we hope will vastly improve the crew comfort and passenger comfort on board compared to the Aurora.
Okay, thanks, Clive. Rosetta Payne, hi Rosetta, asks, what thickness of ice is Nuyina rated to break through? I think that was 1.65 metres at 3 knots.
Yeah, that's right.
Okay, Mike Priestley asks, regarding the crane heeling operability, do you have a rapid ballasting system to counter lifted load, or has a Venturi-type motion control system, or both? Trying to understand the crossover between lift compensation that enhances heli-deck operability.
Yeah, that's fine. So we have a sealed system of, an overpressure, I suppose it's a Venturi system, sealed freshwater system to rapidly transfer water from port to starboard. So as the crane slews across with a load, it will rapidly compensate, keep the ship level, and in doing so, allows us to keep going with helicopter operations. So for example, if we lifted to 3 or 4 or 5 degrees during a lift, we wouldn't be able to operate the helicopter in that situation. So we do have it's a sealed system, it's not ballast, it's a freshwater system.
Right, okay. Craig Bolton asks, did you do any mooring analysis to handle the katabatic winds?
So she's deep there. So we're only intending to moor at Mawson Station, and yes, there has been mooring analysis done at Mawson. All the other stations we have a potential for DP or resupply while locked in ice. In the DP sense, then the strongest winds we've encountered there have been included in the DP analysis.
Right. Mick Dunn asks, what is the freshwater capacity and freshwater production system and capacity?
Yeah, it's a few thousand tons. I forget the number exactly. It's a few thousand tons of freshwater and about that capacity a day, I think. I might have those numbers mixed up. But we have freshwater generators on board, so we can generate our own freshwater and resupply the tanks if we need to. So we have potentially the ability to take down fresh water, but then also we could replenish it by staying longer on station if there was an incident where we lost fresh water on the station.
Okay. Mahinda Nayar asks, what are the dry dock requirements?
Well, I mean, obviously, she's a much heavier ship than a normal 160-metre ship, and the docking loads would be higher. So there is there's always a check on the bottom blocks and the reaction needed on the bottom of the dock to support those docking blocks. Nuyina's problem is going to be the fact that she has a very high concentration of weight over her size. There isn't a viable dry dock in Australia for her, so she will probably have to go internationally to be dry docked. But she does have an in-water survey notation, so she shouldn't be doing it anymore every 5 years. Technically, Garden Island could hold her, but it's more the restriction of the military the priority for military vessels in there that means it wouldn't be viable.
Okay. Carl Linkenbar asks, the ship has a relatively conventional shaft line arrangement with controllable pitch propellers and rudders. Was there any consideration given to podded propulsion?
Yes, that was, I mean, I'm aware from early concepts that was definitely considered. There's a few, the main reason that we were concerned about the ability to perform in ice with podded propulsion, also the ability to handle the ice going astern. That said, I believe my countrymen are building. I think the Attenborough has podded propulsion, but she isn't the same polar class that we are. She's only a PC5, I think, and we're PC3. So I believe that we would probably be fairly unusual in having a podded system on a PC3 icebreaker.
Right. Rosetta Payne asks, how is the vessel stabilised?
So in terms of roll stabilisation, the flume tanks, in terms of cranes, we have, actually the flume system does double up as an anti-roll system for the cranes as well. And the sheer size, we hope, compared to the Aurora.
Right. Arvid Jess Leung asks, in compliance with AS, how do you conduct the planned asset maintenance on a monthly, 3-monthly, biannual and annual basis if the vessel is out in the ocean or in Antarctica and the surface technicians are in Hobart?
Okay, so we have to do careful planning on, I mean, this will obviously still be developed as we go into service, but we do have to do all of our maintenance in a very long maintenance period because the ship is off charter or off active service for a large amount of the year. I think we have 200 or so days of service a year, and the rest is available for maintenance. So we do have that ability to do then, and we carefully plan our routine maintenance to be either early or an exemption given for it to be slightly late in order that we can fit around our program. Because really we do need to be operating when we can, because the window for the Antarctic season is relatively short.
Sure. Rosetta Payne asks, how does the ship deal with waste and rubbish?
Yep. Okay, so we have onboard incinerator for disposal of the waste, or we actually compact it and bring it back to Hobart. Water waste wise, there's a zero discharge in Antarctica rule, so most of our waste has to be retained on board, like grey water or black water, for example, for discharge either through a treatment plant, of course, either outside the Antarctic area or brought back to Hobart. So really, essentially, the main difference between us and a normal ship is that we have a zero discharge in Antarctica to deal with, which means we need a larger holding capacity.
Right. Rosetta Payne asks, are there seafloor survey capabilities and what is the quiet mode for?
Yes, and they are linked. The quiet mode is for the ability to perform subsea work. We just use the forward engine room in the diesel electric mode, which gives us and that's the reason for the silent R equivalent. And that we have several systems on board. We can deploy sonar equipment either through the moon or over the stern, but also we have a built-in USBL, which I forget what that stands for, which is around just after the bow thrusters. So we do have quite a lot of marine subsea systems, and a lot of work has gone into analysing the flow across those for noise and vibration. There are some things that could disturb the result.
Okay. And Arvind Jess Lang asks, do you have service technicians on board the vessel to ensure active maintenance service?
It's essentially the crew, as it would be on a normal ship. So we do have a lot of redundancy, which is an added safety net, but there will be some maintenance at sea, of course, as is any ship.
Okay. And he also asks, does the vessel have its onboard water treatment process like electrochlorination, using salt water to convert into fresh potable drinking water?
Yes, we have water makers on board, yeah. So we have 2 water makers on board, and we have holding tanks as well. So we do have the ability to generate our own distilled water effectively, and then from that distilled water, that goes into a technical freshwater tank, and then from that we can make it into a variety of either science waters or potable water, or we can just use it in its distilled state, which we have other functions. Because there's a lot of systems, science systems, aviation systems, and of course the hotel that all use various different types of water or grades of water. So it's a fairly complicated process.
Okay, thank you. And Mahinda Nayar asks, do you keep any radioactive materials on the vessel, and are there safety and handling issues?
The only, radioactive materials are under the IMDG code if they're cargo. We have some systems, we have some radioactive isotopes that are used for science. They're in our laboratory, so they're handled in a conventional land way, and they're not subject to IMDG because they're part of ship's equipment. If we do need to carry radioactive equipment, then they would be carried in accordance with that convention, really. So nothing is particularly radioactive in a sort of anything but a medical or science basis. So relatively mild radioactive.
Right, okay. And Warwick Malinowski, hi Warwick, says, what steel grades and any special welding technology were used for construction of the vessel?
Yeah, yes, it's E grade generally. So, and it's a lot of high tensile as well. So some of the E grade, some of the EH grade, EH36. And that's mainly for the cold climate, of course. Some of the weld stuff, I'm not an expert in welding, I wouldn't pretend to be, but there were some real challenges with welding the thick plates because of the heat. Also, the ship has twin gondolas for the twin propulsion, and they're very thick cast steel, and they certainly had challenges with keeping them hot enough to weld, so that they just didn't become a giant heat sink. And that was a real challenge, and the guys did have to wear some pretty industrial protective equipment and do very short shifts. So that was a pretty big challenge in terms of that welding. But other than that, I'm not enough of an expert to say, sorry.
Okay, well, that brings us to the end of the questions that I have so far. Does anybody have any further questions? You'll have to speak up, otherwise we'll draw it to a close. Anything, ladies and gentlemen? Well, that pretty much looks like it. Hang on, we've got one final one from Carl Linkenbar. No, we've got several final ones. What is the maximum sea state which the ship can handle?
Yeah, I've got to get my Douglas and my Beauforts right here. Survival mode is pretty much anything that you can throw at, anything that exists. I think sea state 9 is the top one. In a survival mode, because the Southern Ocean is pretty much as bad as it gets for sea state. So we do have a survival mode that the ship should be able to survive in those conditions. So that's the sort of limit really. There is essentially no limit in foreseeable sea state because of the fact that we operate in the Southern Ocean.
Very interesting. I'll make a comment here that there was a very interesting paper presented at Pacific 2019 IMC where they analysed the sea states from measurements taken in the Southern Ocean and found that sea states down there are generally worse than anything that's ever been taken up in the Northern Hemisphere. So that the standard sea states that they apply up in the Northern Hemisphere just aren't good enough for the Southern Ocean.
No, I mean, various scientific organisations, mostly in Hobart, do keep record of this. We're not the only people that operate down there. The investigator goes down there, of course, and other Antarctic programs. I mean, really, anything south of Hobart, until you get to about 60 degrees, can be pretty rough. After that, it tends to calm down as you approach the ice. But yeah, you do see some pretty extreme conditions. And that sort of really summarises the challenge that we have with this project, because the ship has to survive that and comfortably as best as you can in open water, but also be able to ice break in calm, flat, frozen conditions. So it's a real technical challenge.
Sure. Mahinder Nayar asks, are there any special materials used in the hull construction?
All shipbuilding steel, but obviously EH grade. So yeah, higher yield strength steels, all class approved, of course, and to E grade, the temperature rating. Because the ship is the steel structure will spend vast periods in a below freezing almost temperature, so it does need to hold its properties in those conditions.
Right. Well, here's a good question for you. This is from Rosetta Payne, who says, "My 5-year-old son wants to know: has a rabbit ever been taken to Antarctica?"
I don't know the answer to that. The only thing I would say is that we have an eradication program we've had an eradication program for invasive species on Macquarie Island, and there are concerns about Heard Island and invasive species from the whaling and sealing days. So I wouldn't say that anyone does it sensibly, because it is an invasive species. So good question, though. I like it.
It's a good one. And I think this will be almost the last question. Arvind Jeslayung says, what type of coating was used on the vessel to avoid or to prevent corrosion?
Yeah, well, the key area, I mean, above water is fairly standard, to be honest. I mean, it just needs to be temperature resistant to coat being iced up. Under the water is a special sort of coating to reduce the frictional coefficient of the hull. So it is a spray coating, but it needs to be incredibly strong, incredibly well keyed to the hull. And it's, I mean, you learn this a lot from, as a naval architect that didn't work as icebreakers before, you learn a lot about ice coatings and the effect they have, because it has a massive effect on the drag of the ship and the resistance in icebreaking, particularly on the interface with snow on the surface. So it's not just the ice, it's also the snow covering on top and how that interfaces. What you would call our anti-foul line is quite a long way above the maximum draft, because of the fact that the ice and snow piles up on top of the water level, the static water level. Right,
okay. All right, well, I think that's the end of the questions. So many thanks, Clive, for your presentation on behalf of RINA, IMarEST and Engineers Australia, and all the participants this evening.